at hand is whether or not space solar power is achievable, i.e. real operational solar power satellites within a generation. Good. So everyone here, I think, should be familiar with the vision of space solar power, the concept of affordable and abundant solar energy up in space at the power levels of megawatt and greater, and clean, safe, and affordable and virtually limitless solar power here on Earth on demand 24/7. What I'd like to do is take you through a little bit of a historical perspective and a sort of the changes, the evolution in the architectures of solar power satellite systems and pathways to get to the development of solar power satellites in order to illustrate for you why today the opportunity to actually move forward with very large-scale space solar power systems is far more feasible and far more affordable than it was or has been either 30 or 40 years ago or even 10 or 15 years ago. So I'd like to start with some foundations. What were the concepts for space solar power when the idea was being explored in depth in the 1970s? So this is the reference system concept for 1979. It's a large planar photovoltaic array using silicon solar cells without concentration. It's on a very, very large aluminum framework, and it basically is like an extraordinarily large monolithic satellite system. On either end of the platform there on the right, you see large transmitters or transmitter arrays. To give you a feeling for the scope of this single monolithic system, please keep in mind that the small dots from which the microwaves are being transmitted, each of those is 1 kilometer in diameter. And each of those dots, which is 1 kilometer in diameter, had to be, based on the technology and the concepts that were available at the time, held perfectly flat to a fraction of wavelength, so less than a centimeter of deviation across a 1 kilometer object, which was made out of aluminum with a backplane of a high voltage electron tubes, either klystrons or gyrotrons or magnetrons. And that object had to be physically pointed on a large gimbaling system in order to move from one location on the Earth being power to a different market on the Earth. To build this kind of, and the total length at this time, this is the concept at the time, the total size of the solar array for this solar power platform, which would deliver about 10,000 megawatts to the ground, was on the order of 5 kilometers by 20 kilometers, 5 kilometers by 20 kilometers. So a truly stupendously large single monolithic system. So imagine if one were to build a supercomputer using the technology, but with today's capacity, using the technologies and the components that were available in 1970, the data architectures that were available in 1970. But you wanted to build a 10 petaflop machine, or a 1 petaflop machine, with terabytes of accessible memory. But think about the big magnetic force and so on. Think about what that would mean technologically and in terms of the system architecture. Now, to support that, absolutely, and to support that, you had to have truly stupendously large supporting infrastructures. As, for example, in this conceptual diagram, a 2-stage orbit reusable launch vehicle, which would put the pieces up into orbit, which would dwarf the space shuttle, which is now ending nearing the end of its operational life. And this system would be able to put up the enormous pieces of these stupendously large monolithic platforms. Also, to assemble them in space, you had to have enormous in-space platforms. These are the huge factories. This is one concept. To put the piece parts together, it's manufacturing the big solar array that you see here going up and down in the diagram on the right. And it's basically rolling out the structure and piling it with solar cells and so on. And the bottom line was that to get to that monolithic system required a single stupendously large project, analogous to a super Apollo project. So much larger than Apollo. This is the notional roadmap that was discussed around 1980, how to get there. It was a single big project, and ultimately the concept was, the proposal was we'll do that within 20 years, and the first working prototype of a based on this architecture, would take something like $80 billion to build or more. This is sort of the low end of the estimate. And I understand. Well, this is just the first prototype. And the bottom line was, in 1980, and I want to hurry along because of the time, the bottom line was, around 1980, the Office of Technology Assessment in the U.S. Congress at that time and the National Research Council looked at these plans and these concepts and variants on them and said, this is not a practical thing to pursue at this time. And all work in the U.S. was essentially stopped. Now, work continued internationally, technology continued to progress, and in the 1995 timeframe, I was the head of advanced concepts at NASA, and I got the assignment to go back and re-look at space solar power to determine whether or not new technologies and new architectures might make possible new technical approaches that would make space solar power feasible, whereas it had not been feasible in the 1980 timeframe. So we started in 95. A lot of things had changed. The question is it changed? Are they feasible? There were numerous new system architectures that we identified using new technical concepts. The fundamental idea was that because of the revolution in solid-state electronics, which led to the transformation in robotics and sensors and networks and network computing, that modular system elements were now feasible. And that led to a whole range of new concepts which you may have seen in the literature, such as the sun tower concept, the solar clipper, a modular solar electric transportation system, and things like the integrated symmetrical concentrator. The use of robotic construction and the self-assembly of space solar power systems led to a completely new approach to deployment that got rid of the very, very large initial infrastructures, significant improvements in component technologies, particular solid-state devices. Thank you. You said 15 minutes, didn't you? 50? 55, improved component devices, particularly solid-state devices, completely changed the approach to power transmission, in particular using solid-state amplifiers rather than using the big electron tubes with the rigid waveguide structures. And there's a new focus on space applications of the interim steps, whereas before it was this one big monolithic project. The new roadmap, rather than being a single huge monolithic roadmap, project plan, was instead a strategic roadmap with a series of off-ramps, each of which would involve the demonstration of first a 100 kilowatt system, then a megawatt system, then a 10 megawatt system, that would get you from the state of the art, which is about 5 to 10 kilowatt satellites in geostationary Earth orbit, to space solar power system class satellites. The big we went to the National Research Council again 20 years later in 2000, and the fundamental finding of the National Academy of Sciences was, okay, space solar power systems are technically feasible. However, the big issue remains, are they economically viable? And they identified that a number of technical advances had to be made in order to get to the final goal of cost-competitive terrestrial power. And this is, of course, a very long discussion. This should be an entire hour all in of itself. But the bottom line, circa 2000, 2003, was that although we continued low-level SSP-related, space solar power-related R&D for several more years, despite the positive results of the National Research Council review, U.S. activity has stopped again about 3 years later. Now, various reasons. One was the lack of interest by the Bush administration. Another one was the loss of Shuttle Columbia and the whole replanning that led to the vision for space exploration, and the fact that space solar power was not an integral, the delivery of power from Earth, space to Earth was not a part of that. However, international interest continued with some increase, but this was particularly due to the changing energy market, climate change concerns, and so on. Now, today, why is this practical today? Okay, this takes about an hour to explain all in of itself. This diagram, the fundamental message is when you look across the global international landscape, there is a vast number of activities which are related to space solar power, either in R&D or in actual focus activities, both in government, space agencies, and in commercial ventures, both large companies as well as small. The one that I want to highlight here is the International Academy of Astronautics study, which has been going on for the last couple of years. This is going to come out in the spring. It's looked at 3 basic architectures: an update of the microwave classic from the 70s, a modular laser concept, using diode lasers, and the integrated symmetrical sandwich concept, which is a sandwich version of the integrated symmetrical concentrator. The basic concept is a little bit updated. It's not to deliver power from one satellite to one target on the Earth, but to be able to deliver power within a wide field of play on demand in order to satisfy optimal market conditions. The assessment looks across a range of these system concepts and the technologies that are needed for each. That'll be coming out soon. I got 2 minutes left. And there is a fundamentally new roadmap, which is intended to provide an international framework in which you have moving from right to left, time and investment, and from top to bottom, technology readiness, the maturity of the technology, going from basic architecture studies up and through the technology demonstrations, a pilot plant which is identified here, and eventually from the pilot plant into commercial operational systems. The fundamental finding of the Academy, this is in draft, it's still going through the peer review process, but at least of the study group, is that within 10 to 15 years, a pilot plant delivering megawatts of power could in fact be realizable within a finite amount of budget. So, by finite, I should say finite. By finite, that's on the order of $5 to $10 billion, not $100 billion plus. I.e., it's not trivial, this is a big effort, but it's not an impossible amount of money. And the fundamental reason for this is that these new system concepts are all modularized in character, i.e. you can build one piece almost to maturity, and then you put a lot of pieces together. Everybody in the room maybe has one of these. There's a lot of laptops in the room. There are probably more computer systems in the room than there are flesh and blood humans. This is the basic architecture of modern society, network computing, distributed computing. Same thing has to be done if we're ever going to get anywhere with these extremely large space systems. They cannot be monolithic, ENIAC-type systems. So just to close, there are new opportunities, there are lots of international activities, significant changes in the market, lots of advances in component-level technologies. There are continuing challenges, new competitors in ground-based renewables, lack of real end-to-end studies and focused demos. Hopefully the upcoming Academy study will provide a new framework. I'm not going to go through this, obviously, but the key message here is that within 7 to 15 years from today, depending on an investment which doesn't have to exceed that which is now being invested in, say, the James Webb Space Telescope, the Jim Webb Space Telescope class investment by the international community, both industry and space agencies, could in fact realize a subscale but operationally scalable multi-megawatt solar power satellite demo within 7 to 15 years. By 10 to 20 years from today, i.e. within a generation, operational space solar power systems can be realized. So no fundamental breakthroughs in physics are required for space solar power. New approaches are essential, and the key issue is that solar power satellites have to be modular, affordable, scalable, and manufacturable, i.e. you cannot somehow say I'm going to sprinkle pixie dust and later on I'm going to take a monolithic architecture like an ENIAC, like a huge 1960 class mainframe, and I'm going to make it cheap. That's just not going to work. You have to start out with architectures like network computing, which are inherently mass producible, and figure out how to put them together to make extremely large systems in space. Space solar power has the potential to deliver large-scale solar energy from space to global markets up from tens to hundreds to thousands of gigawatts over the coming century. And there are a wide range of strong interim markets for the kinds of systems that would be developed. I know, 200 lines, 300 lines. But I would say that let's just close by saying that the key next steps are to do the kinds of end-to-end system studies that have not been done that would engage the international community, both government and commercial, and to do critical function demonstrations at systems level with increasing levels of development, first in ground labs and in the field of the ground, and then ultimately in space. Thank you very much.